So, hi guys, welcome to V-Numericals. So today we are going to solve. We have BME. Okay, I don't know if you can see. This is BME, Bucharest Technological University for semester one. This is summer exam, and this is a total exam of 70 marks, and we will solve only all those numericals, okay, getting higher values like 7 marks and things like that. So we are going to solve this one. First we will start with summer, then we will go to winter and 2021 exams of BME and 2020 and so on. Okay, for this one, what they ask here, let me see, just it is to derive. They say that derive the characteristic gas equation for a perfect gas with usual notation. Okay, so first thing we have to do is, okay, we are solving for question one. Okay, question one, we are solving for question number one. Question number one, line C. Okay, the first thing we have to do is just to write down here. Okay, here, what do we have here? To derive this characteristic gas equation, we have to combine two very important laws. The first law, it is the Boyle's law. Okay, Boyle's law, that is given as PV equal to C when temperature is constant. So Boyle's law said that pressure of a gas will vary inversely proportional to its volume if I keep constant the temperature of the same gas. And we will combine this Boyle's law with the second law, okay, second law, that is called Charles' law. So Charles' law mathematical expression is T, okay, upon T upon V is constant. Okay, so when T upon V is constant, when pressure is constant. So what Charles' law says? Charles' law says that if I keep constant the volume, or if I keep constant the pressure of a gas, okay, so the temperature of this same gas will vary directly proportional to its volume. It means if I increase the temperature of this gas, the volume will also increase. So from here, it's okay. Now all we have to do, it is just we have to draw PV diagram of this two combined process. I will call this one process one. Okay, this will be state one. Okay, so it's in the first state, and then it isothermally, okay, it is with the same temperature, isothermally expanded. Then from point 2 or state 2, it keep constant the pressure. Okay, the pressure kept constant, and it went to point 3. Okay, now that we have this one, we know that this one is a isothermal expansion. Then here we have another expansion, that is isobaric expansion. Why is it expansion? Because it is increasing. The volume here is increasing. Here volume 1 is less than volume 2. Now let us write what should be this equation in this way. So for the first process, it is an isothermal process. So here we can write P1, the first process. Okay, for the first process, let me write here P1 V1 will be equal to P2 V2. Okay, P2 V2, and T1 is equal to T2. And for the second process, we will have what? We will have T2 upon V2 is equal to T3 upon V3. It is when our pressure 2 is equal to pressure 3. Now, what do we have to do? All we have to do here is just to substitute. Okay, pick up V2 here and substitute in there. Okay, from 1, okay, let me take from 2, from equation 2, we will find what is V2. V2 is Okay, if you just apply this, multiplying this, and this multiplying this, then it will be like this. So our V2 will be in simple words, okay, T2 times V3 upon T3. Okay, then I will call this one 2.1 equation. This 2.1 I will substitute directly to equation number 1. So I will write here 2.1 in 1. How will it be? Okay, 2.1 in 1, it will be P. Okay, let me just adjust here so that you can see home. Okay, what will it be? It will be P. Just substituting this one, it will be P1 V. Okay, V1, it will be equal to P1 V1 equal to P2. And what is V2? V2, it is 1 T2 V3 upon T3. Okay, now from here we know that T2 is equal to T3. Let me write here to T3. Okay, we know this. Okay, we know this true. Okay, we know that this is true. Let me write here so that you can see. You can all see. Okay, T2 is equal to T3. So T2 is equal to T3, and we know that what else we know? We know that P2, okay, T1 is equal to T2. Yeah, now it's okay. And we know that, okay, T1 is equal to T2, and we know that P2 is equal to P3. Nice, according to this one. Here, this one is this one, and this one is this one. If I substitute this one, what I will get? I will get this P1 V1, okay, is equal to P. What is P2? P3. What is T2? T1. So I'll get T1 times V3 times this one upon T3. So T1 must go with this one also. So then just T1 go down. What will I get? I will get P1 V1 upon T1 is equal to P3 V3 upon T3. That is equal to a constant. Okay, that is a constant directly. Okay, hope you can all see this. Okay, hope you are all seeing. Okay, point is this one. So we ended in this way. Okay, that's where we ended. Okay, now you can just grab your points, grab your exercise. Okay, now we find in this. Okay, now what's the next? See, as we finished P, okay, we know that P1 V1 upon T1 is equal to P2 P3 V3 upon T3. Okay, this is true and this is shown is equal to C. It implies, okay, this one implies, what does it imply? It implies that I can just only, for any P, for any state I can draw, okay, I can change this P2 or P1 in P2, P1 and so on. This will be constant. So PV upon T is equal to C. It's independently of the state. Now what we have to do? So this expression here, PV is equal to CT. This C, it's a constant, but this constant depends on the mass of the gas and on the characteristic gas equation. Okay, so C here is a product of M times R, where this M is the mass of the gas and this R its characteristic gas equation, and it varies according to the type of the gas that we are using as in the sample. So we just substitute this one, okay, this one C in this. What we have? P V is equal to M R T. Now we just substitute, we just divide it all by by M, by unit mass M. So here we'll have PV upon M is equal to RT. So V upon M, it is nothing more than our specific volume. So here this equation will end like this, RT. So this one is what we call characteristic gas equation. Okay, there's a difference between characteristic gas equation and what we call this is characteristic gas equation. There's a difference between characteristic gas equation and this another one equation. So here we are done. Okay, till here it's okay, but there's a difference between characteristic gas equation and perfect gas equation. This PV equal to M RT, this is a perfect gas equation, or Clapeyron, how can I say, Mendeleev-Clapeyron equation, or equation for perfect gas. But this one, it's characteristic gas equation, because everything is relying on this constant here. Okay, so thank you. Now it's done.